Transformer models are an innovative architecture in the field of machine learning that have drastically reshaped our approach to natural language processing tasks in recent years. These models revolve around attention mechanisms, an approach introduced in the 2017 paper, Attention is All You Need. In this video, I will give you a comprehensive explanation of how exactly these models are functioning. Before going into the specifics of transformer models, it's worth noting that natural language processing is a field with a long history of various methodologies, including techniques like term frequency inverse document frequency, or TF-IDF, convolutional neural networks, and recurrent neural networks, such as the long short-term memory network. Early NLP methods were largely based on counting the occurrence of words to build classifiers. Although such methods could potentially detect something as an obvious spam email, their inability to capture context prevented them from doing much more than that. Convolutional neural networks and recurrence networks were the go-to approach up to a few years ago. However, they as well had their issues. While they were capable of capturing context, allowing them to tackle more difficult problems, they struggled with capturing long-term relationships within a sequence. This is largely due to the architecture, which tends to favor the learning of short-term patterns. Transformer models were introduced in a 2017 paper from Google addressing the issues previous approaches had. By employing attention mechanisms in their architecture, they circumvented the bias towards short-term relationships and sequences. This paper is widely regarded as one of the most significant in recent decades, laying the foundation for today's popular large language models. Beyond excelling in NLP tasks, transformers have also found applications in time series forecasting, audio processing, and more recently, even image processing. The transformer is a sequence-to-sequence model that operates on an input sequence to generate an output sequence. A typical application might be translating English sentences to German. The left side, or encoder, processes an English sentence, while the right side, or decoder, generates the corresponding German sentence one word at a time. However, most transformer models developed after this paper have only used the encoder or the decoder part, with a few modifications making them more suitable for the specific task. Encoder models like BERT encode the meaning of a text into a compact vector representation, while decoder models like OpenAI's GPT or Meta's Llama autoregressively generate new text. The original transformer architecture is rarely needed, since even a task like translation can be achieved with a decoder model alone. By placing the English text into the decoder and concatenating it with a partially translated German text with a separator symbol in between, the combined text can be treated as a single sequence for generating the next word. Given that encoder-decoder transformers are typically harder to train, most modern architectures opt for decoder-only models. In the following sections, we will go into the specifics of the embedding process and, more importantly, the attention mechanisms, which are the core of the model. With a better understanding of how inputs propagate through the model, we can then explore the training and inference stages of transformer models. So let's begin by answering a fundamental question. How do we pass something as abstract as a sentence into a neural network? A common approach used not only by transformer models but also by other architectures is to define a vocabulary and map each word in that vocabulary to an integer. Once such a mapping is established, we can convert any word from our fixed size vocabulary into a one-hot vector representation. This approach is crucial because if we were to pass the normalized form of the integer representations of our words directly into the model, it would struggle to differentiate between two adjacent words in the vocabulary solely due to the similarity of their numerical representations. By processing the one-hot vector through a linear layer, we can attain a much more condensed representation of a token. For instance, in this scenario, the one-hot vector of size 25 is represented by only 4 floating point numbers after passing through our linear layer. Observe that the highlighted weights in orange carry the embedded values of the input token, given that all other weights are multiplied by 0. This way, vector representations for all tokens can be learned independently. When we train our model on sufficient data, word representations for similar words tend to converge and become more alike. Consequently, the model constructs a meaningful embedding space for all the tokens in its vocabulary. Recurrent networks and convolutional networks naturally incorporate word positions due to their design structure. However, as we will discover later, attention mechanisms don't inherently consider positional information. Therefore, the authors of the paper include a form of positional embedding that is added to the word embeddings. They achieve this in a somewhat complex manner, calculating an embedding value based on the position and the row within the embedding vector. They utilize sine and cosine functions with varying frequencies to do this. In our scenario, where we have embedded our sequence with vectors of size 4, pos signifies the token position in the sequence, and I refers to the row in our embedding matrix. The authors speculated that the sinusoidal embedding would make it easier for the model to access specific locations through attention mechanisms. The figure below shows how such a position embedding looks like for a sequence of length 24 and a vector dimension of 4. However, they also demonstrated that the use of learned position embeddings resulted in a nearly identical performance on the validation data. This method is what OpenAI favored for the GPT-2 model, a popular open source model for text generation that builds on the Attention is All You Need paper, and is a predecessor to the widely popular ChatGPT model from OpenAI. Once we have our position embeddings, we simply add them onto our word embeddings to obtain the final embeddings that will be passed to the rest of our network. It should be emphasized that these positional embeddings are absolutely crucial, since otherwise the model would have no way of knowing the order of the words that are being passed into it. Also, a slight dropout is applied to the sum of the embeddings, which is a regularization technique to avoid overfitting by randomly setting a small fraction, such as 10% of the output, to 0. Before diving into the attention mechanisms, it's important to understand how tokenization, or the process of splitting text into meaningful elements or tokens, is implemented. As an example, models like GPT-2 and GPT-3 use a technique called byte pair encoding, or BPE. In this relatively simple approach, we begin with a corpus of text for which we aim to construct a tokenization. Let's say we have a corpus containing the words dine, hinder, order, and her, which occur 3, 2, 2, and 2 times, respectively. We first deconstruct our words into a set of base characters or symbols from which all words can be constructed. Subsequently, we keep grouping the most frequent pair of symbols in our corpus and add it as a new symbol to our vocabulary. Through this process, we create a vocabulary that comprises individual tokens for frequently occurring words, as well as tokens for frequent syllables and all our base characters. This results in a balanced and efficient vocabulary that can handle a multitude of words and their variations. Using this approach, the creators of GPT-2 managed to produce a vocabulary containing 50,257 unique tokens. Referring back to our initial example sentence, its tokenized form with actual token values from the GPT-2 tokenizer would look like this. Thanks to byte pair encoding, the tokenization process is quite robust, as it also provides representations for various subwords or common sequences of characters. Take for instance if a typo was introduced by adding an extra X to the word example. Given that the token for the misspelled version of example wouldn't exist in the vocabulary, the tokenization of the sentence would now appear slightly different. The introduced hash symbols indicate that the subsequent token isn't the beginning of a new word and therefore doesn't have a space preceding it. This strategy allows the model to flexibly handle different words, subwords, and even unexpected variations of typos in the input. Now we will talk about the attention mechanisms, which are the heart of the transformer models. The figure on the right is a representation of how the attention layer functions. Attention mechanisms take queries, keys, and values as input, all of which are sequences of vectors. The idea is that at each position of the query, we can calculate a weighted average of the values based on the attention calculated between elements of the query and the keys, where each key vector corresponds to one value vector. This might look confusing as of now, so let's start with a simple example. Suppose we have a sequence of 3 vectors which act as our queries, and a sequence of 4 vectors acting as our keys with corresponding 4 value vectors. We want to calculate how much attention each query element pays to the key value pairs by measuring how similar the different query and key vectors are. For that, we calculate a dot product between the query and the key vectors. Dot products can be used as they are generally larger for more similar vectors. If we do this for all possible pairs, we get attention scores between each query key pair. Then we apply the softmax function to every row of this attention matrix, producing normalized scores that sum to 1. This essentially represents the attention distribution for each query over all key value pairs. The final output of the attention mechanism is then computed as a weighted average of the value vectors, using these attention scores as weights. This output will have the same number of columns as our query matrix and the same number of rows as our value matrix. Although the query and the key vectors need to be of the same size, the query and the value vectors don't necessarily have to. This whole process can be expressed concisely through a series of matrix multiplications for efficient computation, as depicted in this formula from the attention paper. Note that this formula assumes the query, key, and value matrices to be in an already transposed form. Also, a square root of dk term is introduced, where dk represents the dimension of the key vector. We divide the attention scores by this term before applying the softmax operation. This is done to counteract the effect of larger dot products when the dimensionality of the key vector increases, thereby preventing the softmax function from becoming too sensitive to small changes in the input. This adjustment enables the attention mechanism to function properly regardless of the key vector size. We still haven't discussed where the query, key, and value matrices actually come from. In the transformer, attention is used at 3 different locations. The encoder attention and the first decoder attention are self-attention mechanisms. In self-attention, query, key, and value are derived from the inputs by using 3 different weight matrices or linear layers that are applied to the input. By transforming the same input into 3 different spaces, we give the model the freedom to attend to information that is not necessarily similar, but rather relevant to some part of the sequence. You can see that if we wouldn't transform the input first, but rather use the input itself as query, key, and value, each word would always pay a lot of attention to itself and other similar words, which would greatly limit the ability of the model. The second attention mechanism in the decoder operates somewhat differently. Here the query comes from the decoder and the key value pairs are derived from the encoder. The output sequence of the attention mechanism is the same length as the query, hence it's logical for the query to come from the decoder. This ensures that the dimensionality of the decoder sequence is preserved, which is necessary for making predictions at all positions within the sequence. By using attention in this way, the decoder calculates a weighted average of the values that are derived from the encoder, based on the attention scores calculated between the query and the key vectors. In the figure on the right, you will see the decoder contains a masked multi-head attention mechanism. Don't worry about this for now, as it will make more sense later when we discuss how these models are trained. However, transformer models don't actually use simple attention mechanisms. Instead, they employ multi-head attention. This means that they have multiple independent attention mechanisms, each having their own query, key, and value transformation matrices. This allows each token to attend to a variety of different concepts more easily. The outputs of all of the attention mechanisms are then concatenated along the value dimension and passed through a linear layer, which usually serves to reduce the dimensionality. In this example, we see 3 attention heads, but the number of heads can even go up to something like 96 in super large models such as GPT-3. The encoder and decoder blocks in transformers share a similar structure with some key differences. The encoder block consists of 2 sublayers. In the first sublayer, multi-head attention is applied, followed by adding the input to the output and normalizing the result. This normalization step ensures that the vector at each position has a mean close to 0 and a standard deviation close to 1, contributing to the stability and effective learning. The second sublayer of the encoder block contains a linear layer with a ReLU activation, followed by another linear layer. These linear layers are applied to the vectors at all positions equally. The output of this sublayer is added to the input, resulting in the final output of the encoder block. The purpose of this design is to allow the model to capture both local and global dependencies in the input sequence. These residual connections or skip connections that add the input to the output play a crucial role in the model's learning process. They address the problem of vanishing gradients, which becomes significant in very deep networks. As the gradient is backpropagated through many layers during training, it can become too small to effectively update the weights. By providing a shortcut for the gradient to flow through, residual connections allow the learning to continue effectively. Similar to the sum of the word and position embeddings, dropout is applied to the output of each sublayer before adding and normalizing. In decoder blocks of encoder-decoder architectures, there is an additional multi-head attention layer with a residual skip connection and layer normalization after the first sublayer. This extra attention layer enables the decoder to access information from both the previous layers and the encoder, facilitating the generation of meaningful predictions. Only encoder-decoder transformers have this extra attention layer, since decoder-only architectures don't have an encoder part. For the residual connections to work, the output layer of each multi-head attention transforms the concatenated values to the same dimensionality as the input. Like this, the vector dimensions at any position stays the same throughout the entire model, from embedding up until the last layer where probabilities for the next token are generated from the output. These encoder and decoder blocks are then arranged in a sequential stack n times. Each stack is a separate instance of the encoder or decoder block with its own set of weights. For instance, the largest GPT-3 model uses 96 stacked decoder blocks. In encoder-decoder architectures, the output of the final encoder block is used to derive the keys and values for the decoder blocks during the encoder-decoder attention stage. Modern language models, such as GPT and its variations, often use only encoder or decoder blocks, with varying approaches to those proposed in the original transformer paper. After the decoder blocks, the output is passed through a final linear layer. In the paper, the weights for this layer are the transposed embedding weight matrices used to embed the input and output sequences. While this might seem counterintuitive, as the transposed matrix doesn't act as an inverted matrix, it's been argued that this approach can reduce model complexity while maintaining comparable performance. However, it's worth noting that this kind of weight tying is not essential and the model would also work without it. This final layer is applied to all positions equally and transforms the final decoder output into a matrix containing vectors of next token probabilities for each position. Therefore, if a sequence of length 20 is input into a GPT-2 model with 50,257 tokens in the vocabulary, the model will output a 20 by 50,257 matrix containing the next token probabilities over the vocabulary for each position. Most transformer models undergo an initial stage of unsupervised pre-training before they are used or fine-tuned for specific tasks. BERT, one of the first widely used encoder models, is trained by predicting missing positions in gap texts and determining the order of two given sentences. GPT, one of the first popular decoder models, is trained to predict the next token in a sequence. The key advantage of both of these models is their ability to be trained on massive amounts of data without active labeling. This is because labels for gap text prediction and next word prediction can be generated automatically. These training tasks encourage the model to gain a deep understanding of language and human concepts, resulting in impressive performance. For encoder models like BERT, we can construct classifiers on top of the model's output, as this output represents a condensed version of the input sentence. On the other hand, decoder models like GPT are used in applications such as chatbots or text generators. They are trained using a shifted version of the input sequence as labels for each position. Given an arbitrary text, the model is tasked to predict the next token and is trained using a cross-entropy loss function which compares the actual tokens to the predicted probabilities. One issue, however, is that, so far, nothing prevents the decoder from just cheating and looking forward in the output sequence to obtain the next token at a previous position. This is why we use masked attention in the self-attention layer of decoder blocks. Let's consider our sequence and its token values from earlier. If we just were to put in the sentence like this and give it the according labels, the model would be able to look forward in the sequence to obtain the next token. However, this undermines the model's need to truly understand the language patterns and dependencies within the sequence. To prevent this, we utilize a masking mechanism in the self-attention layer of the decoder block. limiting the information flow from future positions. Consider a mask for an input sequence of length 8, as shown on the right. This mask determines the extent to which a position at row I can attend to a position at column J. By multiplying the resulting attention scores with this mask, we can prevent the model from looking forward because there is no information flow from later to earlier positions. To maintain the correct probability distribution, we rescale the probabilities so they sum to 1 across the value positions. This process makes training highly efficient, as we can pass an entire sequence to the model at once. Therefore, we need just one forward and backward pass per sequence. When it comes to inference, for each new token that is generated, we need to perform a forward pass for all previous tokens up until that point. This can make inference highly computationally demanding and time-consuming. You might notice that a substantial amount of computation power seems to be wasted after the first forward pass, because the distributions for all previous tokens are calculated again, even though they are not needed anymore. However, we can't just simply disregard these calculations because the internal hidden states at these positions are needed for generating the next token. One possibility to save some computational resources could be to disregard these positions only after they have passed through the last attention mechanism. This is because beyond this point, their states are no longer relevant to future positions. However, in reality, this modification would only result in a minimal speedup. For these reasons, inference with transformer models can be computationally intensive, especially when dealing with larger sequences. Another point we haven't discussed yet is how we actually select the next token once we have the predicted probabilities. Let's say xn is the probability distribution for the next token. We could just use this distribution to sample a token at random based on the probabilities. However, in practice, different techniques are often employed to enhance the quality of the generated text. These techniques include top k sampling, where we only consider the top k most probable tokens, top p sampling, where we only consider the top tokens whose combined probabilities surpass a certain threshold, and temperature adjustment, where we tweak the probability distribution. In temperature adjustment, as the temperature approaches 0, the output becomes more deterministic, and the model tends to always output the most likely token. On the contrary, when the temperature approaches infinity, all tokens become equally probable, making the output more unpredictable and in some cases more interesting. Now, these concepts apply to training and inference of decoder models, but similar principles will also apply to encoder-decoder architectures. As previously mentioned, encoder models are trained slightly differently by predicting gap texts. They are generally not used for text generation, but rather text classification. The core idea behind encoder models is that after such a model is trained, you can build a new classifier net on top of the model's output. This newly built classifier can then be trained on tasks like spam detection or sentiment analysis. ChatGPT, which utilizes a decoder model architecture, has become notably popular as a chatbot with remarkable capabilities. A simple method to transform a decoder model into a chatbot involves prompt engineering. With prompt engineering, the weights of the model are left unchanged. Instead, specific prompts are designed to steer the model's output in a certain direction. In the context of a chatbot, you could construct an initial dialogue between a bot and a human, present this dialogue to the decoder model, and let it generate the next tokens. Since it's trained to predict the next token based on its training data, which includes conversations, it can predict the next token as if it was partaking in a typical chat between a bot and a human. We can halt the prediction process whenever the bot predicts a predefined stop token or a separator sequence such as ###human, signaling that the bot has completed its turn and it's time for the human to respond. However, more advanced methods exist for creating chatbots from decoder models, which involve further training and fine-tuning the model using complex techniques. This often becomes necessary because in the setting we've described, it's challenging to impose guidelines on the bot's behavior. For instance, ensuring that the bot consistently behaves in a friendly and factual manner can be difficult, and there's a risk that it might produce dangerous or misleading information. Consequently, many techniques focus on improving the alignment of these models to ensure they behave as desired. Once the model's basic capabilities are established, there are a variety of ways to enhance their behavior and output quality. I will be covering these more advanced methods in future videos, so be sure to subscribe to not miss out. If you found this video helpful, please give it a thumbs up and share it. Thanks for watching, and don't hesitate to ask any questions in the comment section.